It is 8:30. Okay, guys. 8:30. Time to get started. All right. Good morning, everyone. I'm a little bit rushed this morning. Had to get some stuff ready for my other class and ran into some technical difficulties that I managed to fix at the very last minute, but everything seems to be working fine. Okay, so I don't have any other business other than what I told you yesterday. The chapter 4 homework is out there and due, and I think the acceleration lab, that was, what was that? Hold on, let me double check that one. I'm getting all my stuff confused. Okay, come on. What's wrong with Canvas? Why won't you? There we go. Okay. Yeah, that was due yesterday, so hopefully you did it. All right, so we're moving on. We're doing this stuff on uniform circular motion, and I'm going to do two example problems today, and that'll be it for the example problems for uniform circular motion. And it is Thursday, so next time I see you will be Monday, and we'll move on with the last topic in the chapter, which is called relative motion at that point. We'll start that on Monday. All right, so two example problems for today. So I may not go that long today. So uniform circular motion, right? Again, this is still part of kinematics at this point, right? Kinematics is the topic where we keep track of the motion of an object over time. The three quantities, of course, are, as I've explained many times, the position as a function of time, the position of an object, where it's located, the velocity of the object over time, that's a rate of change of the position, and then the acceleration of the object, which is the rate of change of velocity. Okay, and that's the three quantities we use to keep track of the motion of the object. And so in one dimension, it was pretty straightforward. You're just moving back and forth along a straight line. And in this chapter 4, we went into motion in 2 dimensions. So we allowed the object to move both in the x and y direction for time. And so that allowed, in chapter 1, we only allowed the object to move back and forth along the line. So the direction of the object's motion was only either in the positive direction or the negative direction. There was no angle involved. So technically speaking, it wasn't necessarily a vector quantity in terms of the direction. In chapter 4, we kind of opened up that possibility and allowed for vector quantities. In fact, all the stuff that we did, I told you to think about as components of a vector, even though we didn't do the vector mathematics. But in 2-dimensional motion, like you throw something off a cliff, so if you take a look at, say the velocity vector, the velocity vector would change both its magnitude and direction as it fell to the ground, okay? And then in uniform circular motion, I describe it as a kind of a unique motion in that it's kind of like the opposite of chapter 2. The object's velocity changes, so that therefore there's an acceleration, but it changes in such a way that the magnitude of the velocity vector stays the same, the speed stays the same, only its direction changes. And its direction constantly changes, and it has an acceleration by virtue of the change of the direction of the velocity vector, not the magnitude. And so that happens when an object moves around a circle at a uniform rate. Okay, so hopefully you got that conceptual idea down yesterday, or day before yesterday, or whenever we last met. Yeah, day before yesterday. Still not used to this block schedule. All right, so here is another problem involving this uniform circular motion. One of the main takeaways we got from the last time we met was that the acceleration when it comes to uniform circular motion was a specific type of motion called centripetal, certain type of acceleration. So a certain type of acceleration called centripetal acceleration, which, you know, there's different ways of looking at it. It's either a cause or an effect. If you want something to move in a circle, you have to give it a centripetal type acceleration, according to the equations. If it is moving in a circle, then you know it must be undergoing a centripetal acceleration. And so we got down, we grinded through, and we, in vector form, IJK notation, we derived the position vector, the velocity vector, and then the acceleration vector in vector form. And then one thing we did was took the magnitude of the acceleration vector expression, and if you strip out and just look at the magnitudes, then we got a couple of different equations that are almost like to the point where you kind of need to almost memorize those guys, because they will be, and when we get back to chapter 6, and we start talking about forces, we'll start talking about the forces on objects that are moving in a circle or along a circular path. And so we'll have to involve that in the problem solving. And so the two magnitude equations we got was that the centripetal acceleration was equal to omega squared r. That's the angular speed, or the angular velocity squared times the radius. R, was, when we originally derived it, r was the position vector, but that's the position of something moving around in a circle. And so the magnitude of that vector is just going to be the radius of the circle. So you can now start thinking about, in magnitude terms, about that r being the radius of the circle. Okay, and then we did a little bit more manipulation, mathematical manipulation, and came up with a similar expression for centripetal acceleration, which was v squared divided by r, v squared over r. And that was the centripetal acceleration, but written in terms of the linear velocity v, the magnitude, or the speed, basically, the magnitude of the velocity vector, squared divided by the radius again. You think about r in that case as being the radius. Okay, and we did a couple example problems yesterday using those formulas. Use another one today, use that kind of same thing today in this little first example problem, which I think is kind of a little bit interesting. All right, so I mentioned this yesterday, I think. When we're doing projectile motion problems, you slapped a XY coordinate system somewhere on the problem. You said, oh, that coordinate system is fixed and not moving. Of course, that completely neglects the fact that, we're sitting here on the Earth, and in reality, the Earth is actually a big sphere that it's rotating around its axis. So we're on the sphere, so we're rotating around that axis too in a ginormous circle. And then to top it all off, the Earth rotates around the sun in a ginormous circle. So we're rotating around the sun on a thing that's rotating around its own axis. And if that wasn't enough, the axis itself, as it rotates around the sun of the Earth, actually precesses. That means that the whole thing wobbles. And if you were to look at the axis, it would kind of like wobble around, kind of like this. If that was the axis of the Earth as it goes around the sun. So our actual motion as we go around the sun is actually pretty crazy. We're wobbling, rotating around in a circle, and then all of that is rotating around the sun. So we don't even notice it because that motion's pretty slow compared to everything else that's affecting us, especially, the acceleration of gravity. But anyway, speaking of the acceleration of gravity, what would the acceleration of a person be at the center on our position on the Earth? What would be the acceleration at a person where we're sitting here in the kind of Los Angeles area on the Earth? As it goes around in a circle. And now you have to kind of back up a little bit here and explain a little bit more. We're stuck here at about 40 degrees. I think it's latitude. I can never get latitude and longitude straight. Latitude goes up from the equator, or which one goes around the Earth? Which one goes up towards and away from the North Pole? Latitude is I know, but you could put the ladder either way. That one never worked for me. Latitude. I think it's latitude. I think it's 40 degrees latitude. But anyway, it's 40 degrees as measured up from the equator. So if you think about it, that's a giant circle that we're rotating around in. And the question becomes, forget about Earth's gravity. Forget about the gravity due to that force of gravity, the fundamental force of gravity that causes that 9.8 meters per second squared acceleration downwards. That acceleration is due to a force, which is has nothing to do with this kinematic stuff. It's a force, fundamental force of nature due to the fact that we have mass and the Earth has mass, and nature says there's a force that pulls us together. Ignoring that, ignoring the force of gravity, ignoring the acceleration due to gravity, if we're just sitting and going around that circle, what would the acceleration be? What centripetal acceleration would be necessary to make you move around that circle at the speed we're traveling around the Earth at? That's the question. And so also a little bit of geometry and some knowledge of, like, well, you know, how many you know, hours in a day and minutes in an hour and that sort of thing. Okay, so step one, we're going to need to know the radius of our motion. And if you think about it, our radius of motion for us at 40 degrees up from the equator is not going to be the radius of the Earth. If we were down at the equator, our radius would be the radius of the Earth. But since we're up higher up, our radius is going to be slightly smaller. Do you see how that works geometrically? Okay. Here's a sideways look. If you do a cross section of the Earth, okay, I slice the Earth in half through the center of the Earth, through the axis of the Earth, and I'm placing the axis vertically. So this dashed line here is the axis of the Earth that we are rotating around, right? And we're looking, you know, at the flat cutaway, okay? So here would be the equator. We're 40 degrees up, so we're actually up here, okay? And I think you can see that the radius of the Earth would be all the way out here, but our radius would be somewhat less than that at 40 degrees. Did that make sense to everybody? Hopefully, okay, good. So no other questions about that? It's you got to put on your geometry hat here. Sometimes it's a little bit hard to conceptualize, okay? Okay, so cutaway view of the Earth. We're looking at it from the side. Here's the North Pole up here. Here's the South Pole down here. And we're at 40 degrees up from the equator. Okay, so how can I find our radius? Well, our radius would be from here horizontally into the axis of the Earth, right? Because if we're on a sphere that's rotating, we're rotating around basically a plane defined by a cross section through where we're located, right? Not at the equator, but where we're located. So I think you can see that the circle we're moving around in is a circle, but it's not going to be the same radius. So the radius would be from here into the axis of the Earth, which would be the same as the side of this right triangle, right? Now the distance from the center of the Earth, here's the center of the Earth, out to where we are at, assuming the Earth is completely perfectly spherical, of course, is just the radius of the Earth. We're assuming the Earth is a perfect sphere in this case. All right. So does everybody understand how that right triangle works? No questions about that? All right, we will move on from there then. Hopefully this makes sense. All right, so first things first, figure out what the radius of what we are, r sub m. Why did I call it, what, m, r sub m? Me, my radius? I don't know what I used the subscript m meant. How about r sub me? My radius. Okay, it's going to be, as you can see, you know, from the trigonometry. Notice that this trigonometry comes in all the time in this stuff. So you can take the hypotenuse is the radius of the Earth. The adjacent side to the angle is r sub m. So it's just like ax equals a cosine theta. You know, we're finding the projection on the x-axis. It's almost exactly the same thing. exactly the same math. So r sub e times the cosine of 40. If you remember, you can find the radius, usually they refer to it as the mean radius of the Earth, the average radius of the Earth. But the Earth doesn't bulge that much. So it's not that big a deal. We can just go ahead and use the average radius of the Earth. So 6.37 times 10 to the 6 meters for the radius of the Earth times the cosine of 40 gives you 4.9 times 6 meters, and that's the radius we're rotating around right now. Our radius of our motion right now is 4.9 million meters, and you go around that circle once every day. All right. Now, where do you go from here? All right. This is the same math as we did on the previous two problems, so I'm not going to belabor it too much. There's that omega squared r formula for the magnitude of the centripetal acceleration necessary to make us move around that circle. I'm going to replace the omega, the angular speed, with the angle of one revolution, 2 pi in radians, divided by the time to go around a circle, which is the period of our motion, which would be 1 day, right? If you take 1 day and you do a unit conversion into seconds, 1 day is 86,400 seconds. So like 1 day times what? 24 hours divided by 1 day divided by 60 minutes per 1 hour divided by 60, sorry, times 60 seconds per 1 minute, right? You guys can do the unit conversions, right? Okay, anybody need any help on the unit conversion? 1 day is 86,400 seconds. Okay, and then you put in R, which we just calculated. And so it turns out that in order to move around in a circle that we're moving around in here, in Fountain Valley, you need right around 0.026 meters per second squared of acceleration. Not very much compared to what we're actually experiencing that's making us stick to the ground, right? Remember that I did that problem yesterday where I said, well, if you're at the equator, how fast would the Earth, how fast would you have to be going? How fast would the Earth have to be rotating in order for you to float? So basically that's what this thing is saying. In order for us to just barely have enough acceleration to move around that circle at the radius we're going at and at the speed we're going at, what acceleration would we'd be experiencing if we were like in a space station orbiting around some planet, and we're just floating there, just barely enough acceleration to make us move around the circle, nothing more. It wouldn't be that much compared to like the 9.8 meters per second squared we're experiencing. So you can see how the numbers work out. The amount of acceleration we experience here on the Earth's surface is way more than what we need to keep us stuck to the Earth's surface. Does that kind of make sense here? All right, any questions? No? Okay. All right, so that wasn't too bad. A little bit of geometry, right? Move that guy away. Okay, now I'm going to do a really complicated problem. Okay, and this one, this one you may have questions on. All right, so here's the problem. Okay, put it up there and let you guys read it. All right, so it's the same problem. You've got an object that's moving around a circle in uniform circular motion. Here it is, particle P, point P, and that's supposed to be an R there. Zoom in a little bit. You can. Nope, you still can't see it very well. The copy is just not very good. There's a particle P travels around with a constant speed on a circle, radius R, and it gives you a bunch of information there. The radius of the circle is 3 meters, completes 1 revolution in 20 seconds. Where have we heard that one before? So what does the 20 seconds mean? 1 revolution in 20 seconds. So in other words, what is 20 seconds? Remember that? Yeah, the period, exactly. Okay, so that that you should spot immediately, like, aha. So capital T is 20. So I got something I can plug in. Now here comes the hard part. The particle passes through O, and you look down on the drawing, O is the origin of the coordinate system that they've set up for you. They have an XY coordinate system. X is still horizontal, Y is still vertical, but they shifted the origin away from the center of the circle. And I think I told you when we started this whole thing the other day with doing the notes and trying to derive the position equation. I said the only sensible place to put, the only sensible place to put the origin is at the center of the circle. If you don't do that, life becomes miserable. So I'm going to show you how life becomes miserable by shifting the origin down to not the center of the circle, but the bottom of the circle. Okay. And you got to read the question carefully. Okay, the particle passes through the origin at t = 0. That alone is going to make things miserable. Okay, so find the magnitude and direction of each of the following vectors with respect to O. Does that make sense what they're asking? Find each of the following vectors with respect to O. So now the position vector, which they've got the rate, as they've labeled this radius r here, but that's not going to be our position vector anymore. Okay, our position vector's got to start from O and point to P. Yuck. Okay, so this is just kind of like an exercise in just math. You know, it's like you got to be the Arnold Schwarzenegger of vector mathematics. The position, well, that's what we have to figure out. We have to, you know how we set up R in IJK notation? We're going to have to reset up R in IJK notation in the new coordinate system. So it's not, well, I'm not going to throw the baby out with the bathwater. I'm going to actually use what we did before, but we're going to have to kind of we're going to have to kludge some mathematics onto it. All right, so find that with respect to t = 5 seconds, 10.5 seconds, 10 seconds. For the 5-second interval, from the end of the 5th second to the end of the 10th second, find the particles. B, displacement, and that's going to be a displacement vector, okay, that you're going to have to figure out. And then we'll probably find the magnitude of it. The average velocity, okay, they use that word average now, not the instantaneous. Okay, the average velocity, okay? And then D, find its velocity and acceleration at the beginning and end of that 5-second interval. Okay, so when they don't say average velocity, you have to, this is kind of, they really should have said instantaneous velocity and instantaneous acceleration. That's what they meant. But that's kind of like there's some things that you got to just kind of assume. If they don't say average velocity and they say velocity, you got to kind of assume instantaneous velocity. All right, so a whole bunch of work we got to get done. So there's a lot of setup and a lot of work. This is going to take a while. All right, so where do you start with this mess? And let's make a little drawing of this guy. Let me move this up. Actually, I don't have room for it. So I've kind of redrawn it here anyway. Okay, so there's the redrawing of it, but I've added a few things. Okay, what we are trying to do in this problem to start with is come up with this vector r, position vector r, that starts at the origin down here and points to the particle here. Okay, now how do you do that? Well, you could just kind of do it from scratch, and it would be a little on the messy side, but you could probably do it by brute force. But I'm going to be clever. Okay. In the notes we have previously come up with that vector r sub a, where the origin was at the center of the circle, right? We came up with that. Remember, vectors, you know, this is kind of the way where you can use vector mathematics to your advantage. Since we already have that vector a in the coordinate system from the center of the circle, in this new coordinate system, how can I get that vector r? And the answer is, what if I were to construct a vector r sub 0 here that goes from the origin to the center of the circle? If I add r sub a to the end of r sub 0, vectorially, that should be equal to r, right? Vector a plus vector b equals vector c, like when we did, remember when we did the graphic addition of vectors? Remember that stuff? Okay, so you can see that you add r sub a to the end of r sub 0, and then complete the triangle, and that's the resultant vector. So the vector r is must always be equal to r sub 0 plus r sub a. All right. So that works out just from a purely vector point of view, but there's some little nitty-gritty details that you run into trouble with. Okay, so from the notes, right, this is what we came up with in the notes, that the position vector as measured from the origin, where the center of the circle is the origin, right, from the center of the circle, is r cosine omega t plus r sine omega t, right? Remember that? However, there's two things that we got. There's a little problem with this. When t equals 0, what direction is RA pointing? No. Think again. Remember when we set it up, we measured the angle from the positive x direction, which at the center of the circle is that way. Okay? Does that make sense? Remember that? So, I mean, just plug in t equals 0. What do you get? If t equals 0, sine of 0 is 0. This term goes away. If t equals 0 here, cosine of 0 is 1, and you get 1 times I. 1 times, sorry, not 1. It's 1 times r times I. So it's r times I. So it's the radius of the circle is the magnitude, and it points in the I direction. So r sub a would point to the right at t equals 0. But that would make r completely wrong, because r has got to be here at t equals 0. You get what I'm saying? That makes sense to me? Does that make sense? So which direction does r sub a have to point in so that r sub 0 plus r sub a equals 0? Is this making sense here? R sub 0 plus r sub a pointing in what direction equals 0? What direction does r sub a have to be pointing at in order for this to work out with the initial conditions, they say? Nobody gets it? I don't think anybody. I think people are afraid to answer because this is complicated. If I take a and I subtract a, I get 0, right? So if I take r0 and subtract r0, I get 0, right? So what does minus r sub 0 look like? R sub 0 is a vector that points straight upwards. Negative r sub 0 would be a vector that points downwards, right? So basically r sub a is going to be a vector that always has a magnitude of r, the radius of the circle. But r sub a just rotates around in a circle. So we want r sub a to be pointing straight downwards at t equals 0. So these are cosine and sine functions, right? Do you remember? I don't know. I can't remember what they call it in math class. In physics, we call it a phase shift. Remember that business of shifting cosine and sine functions backwards and forwards along the horizontal axis? And you put in you add a little constant in here. Yeah. Okay. So if r sub a is a vector that points in this direction, and we want to shift it so that it goes backwards a quarter of a circle, what do we have to do? Okay, we're going to have to put in a phase shift, right, to shift that thing backwards. Okay, now before I do that, this is obvious, right? It tells you that the radius of the circle is 3, right? So r sub 0 is a fixed vector that only points upwards in the j direction and has a magnitude of 3. So r sub 0 should be 3j. I think that should be fairly obvious, right? Okay. But this phase business, r sub a must point downwards at t equals 0. So how can I, and hopefully, do you guys know that this whole sine and cosine stuff, all that mathematics is what's the word I want? Really based on the mathematics of something moving around in a circle. Did you know that? I don't know if they get into that in math class. It's a big deal in physics because, like, you know, when something moves around a circle, it's if you keep track of just the vertical motion of the object as it moves around in a circle, it's exactly the same motion as if you put a mass on a spring and you make the mass in the spring bounce up and down. So the y component of this guy, as you move around in a circle, if you keep track of just the position along the y-axis, that moves up and down exactly the same way a mass bouncing up and down in a spring would move. And so that mathematics is the same mathematics. So what I can do is I can take that r sub a vector, which we've set up at t equals 0 points that way, and just put in subtract pi over 2. And by subtracting pi over 2, we subtract a quarter of a circle in angle-wise. Remember, when you take the cosine of the argument of a cosine is an angle. So I take omega t and subtract pi over 2. Okay, so now look at this. If that doesn't make sense to you, just look at it mathematically. If t equals 0, what is this guy? That's 0. What's the sign of minus pi over 2? And the answer is -1. Yeah, so it'd be negative rj. That'd be a vector that points from the origin down towards the bottom of the circle. If t equals 0 here, that goes away. What's the cosine of negative pi over 2? 0, right. So this whole term's gone. So r of 0 for this guy, r of 0 is now negative rj. Compare that with, which would, and r is 3, so it'd be negative 3j. r0 is 3j. This is now going to be negative 3j. 3j minus 3j is 0. So we've got this thing set up so that when we add r0 to ra, it works exactly like we want it to. That kind of makes sense? Boy, that was some impressive math. Okay. All right. So, putting it all together, right? It's that graphic interpretation I was talking about. R as a vector, the position vector should be R0 plus RA, no matter where RA is. Okay. And you get that mess right there, but it works. It may be ugly, but it works. Okay. Any questions so far? All right, moving right along. Okay, now one other thing we need to know when we're actually going to be plugging numbers into this R vector and finding out stuff. And so one of the things we're going to need to know is what is omega? What is the angular speed? Well, remember we got t, right? And omega is 2 pi over t, right? Remember that? Omega equals 2 pi over t. We just did that a second ago. So 2 pi radians over 20 seconds gives us 10 over pi radians per second. Make sense? All right. Keep that on. All right, so just plug in the numbers. Okay, what's R of 5? Because that's the first thing they ask for. What is the position vector at t equals 5 seconds? Okay, and if you plug in 5, just plug that in the equations, and you'll get 3i plus 3j. Okay, which some of you may go, yeah, that's kind of obvious because it's 20 seconds to go around the entire circle, right? So where is it at 5 seconds? 1/4 of the time. Well, it's right over here. So 3 up, 3 over. 3i, 3j. Okay, and you're probably going, why did you make us do all that work? We could have done that immediately. Well, what about 7.5 seconds? You gonna figure that one out? You could probably, using the sine and cosine of 45 degrees, but whatever. Now you can just plug the numbers in. Okay. Any questions on that one? All right. Can you, considering R of 5, could you also give me R of, what is it, 10 seconds? Can you just do that in your head from the geometry and the circle and stuff? R of 10 seconds. The radius is 3. Yeah, there you go. Right. Whoops, it's on the next page. Hold on. Hold on. Okay. So, right. And just for the heck of it, plug in, 10 seconds into our equation up there. And, you'll find out that it goes to 0 and that the other one goes to 3. Okay? All right. So that's the first part. Okay, so what's next on the agenda here? Move this stuff up a little bit. Okay, so position vector at 5, 7.5, 10 seconds. Okay. For the 5-second interval to the end of the 5th, for the 5-second interval from the end of the 5th to the end of the 10 seconds, what's the particle's displacement and average velocity? Okay. So where do you go from here? In other words, displacement, right? This is where you got to go back and remember, your definitions. Okay. Displacement means a very specific thing. It means delta r. Okay. In this case, it's a vector, so it's delta r as a vector. You have to be careful. So deltas always mean the same thing. So the final something minus the initial something. So it's r, the instantaneous position, r of 10, minus the instantaneous position, r of 5. Okay? Well, we have r of 5 and we have r of 10 sitting there, so just subtract them vectorially. Now, do you remember how to subtract stuff in vector form? If you add things, and if you add two vectors, sorry, in IJK notation, if you add two vectors in IJK notation, you simply add the x components together, and that's the new x component. And then you add the two y components together, right? Same thing. Well, subtracting, you just subtract the components. So it's going to be 0 minus 3 and 6 minus 3. That makes sense? And those are going to be the I and j components. So 0 minus 3 is minus 3, 6 minus 3 is positive 3. And again, you could probably look at the picture and kind of figure it out because they picked the easy ones. Okay, any questions on that? No? All right. We'll move right along then. Okay, so now average velocity. Okay, average velocity, you have to go back to the definitions again. We're not adding numbers and dividing by the number of numbers. That is not what average velocity is. It's the displacement, whatever it is, the total displacement divided by the total time. Delta, in this case, r, because that's the position vector, delta r divided by delta t. Okay, so I already got delta r. Now I just got to divide it by the time interval. So does this make sense that you could just divide through, you just divide the whole vector by 5, and so it's dividing each component by 5? Yeah, makes sense? Okay. Yeah, I did get lazy with this problem, didn't I? Everything's in meters and seconds. Okay, I really should have written this guy as -3 meters I and -3 meters J, and this guy should have been -3/5 meters per second I and -3/5 meters per second J, but I got a little bit lazy. This is more of a vector problem than, work out the units stuff. That's why, you notice I haven't been bothering with significant figures. It's just an extra added layer of complexity, and this stuff's hard enough as it is. So I'm not bothering with like significant digits and units is mostly important when you're in a laboratory setting and you're actually doing measurements of real world things, because then you have to worry about the precision and the accuracy of what you're doing, and you got to worry about, and that ends up in the numbers, and you got to, when you're making measurements of numbers, you got to really be careful about how you treat the numbers, because the accuracy and the precision of the device you're measuring with come into play in a big way. These are all made up. These are just academic exercises, so they're tough to understand enough as it is. So I'm kind of skipping. A lot of physics teachers would criticize me for this, saying, no, that's important, you should be doing that. But just in the interest of, I think this stuff is hard enough as it is to be worrying about things like significant digits. It doesn't add anything to helping you understand what's going on. Okay. All right. What am I supposed to be doing next? I forgot what I'm supposed to be doing next. Find the particle's displacement and average velocity. Okay, I think we're done with that, right? Well, actually, maybe did I do the? Oh yeah, I took the magnitude. I should have taken the magnitude of this guy for also. So what? 3 squared plus 3 squared is 9 plus 9 is 18. So it's the square root of 18 is the displacement magnitude. I should put that in. Anyways, the magnitude of the velocity vector is square that, atom, take the square root, right? Did everybody, am I fooling anybody by that? Technically speaking, they ask what the displacement is. Okay. The displacement is a vector, delta r. They didn't really say explicitly what's the magnitude of the displacement. They just said what's the displacement. So, you could technically just say that is a correct answer for the way you stated the problem. And that is the correct answer the way you stated the problem. But a lot of times the authors mean the magnitude, but then they don't bother to put the word in. Anyways, you get the idea? Anybody? Does that fool anybody? Okay. All right. Where am I? Average displacement, average velocity, got that. Okay, D and E. Find what should be labeled the instantaneous velocity and instantaneous acceleration at the beginning and end of that 5-second interval. Okay, how do you get this guy? There's a couple different ways of doing it. If you really know what you're doing, you can kind of kludge an answer together because of the specific times that they're asking for. If you're not really clear, what you can always do is go back up and say, okay, R is this entire equation here in IJK notation as a function of time, right? So what would V as a function of time, b? How can I get v from vector v as a function of time from vector r as a function of time? That you should know at this point. Yeah, right. Take the time derivative of it. So take the time derivative of this guy, and that'll give you the velocity at any point. It's not that bad. It's really not that bad. You think, oh my God, this is horrible. But remember what we did? This is just taking the derivative of a vector. And what do? You just take the derivative of each one of those components, and those are the components of the derivative, right? The derivative will distribute across the ijk sum. So what's the derivative of this guy? Well, the r is a constant. It comes outside. The derivative of cosine, this is a function inside a function, so we will have to use the chain rule. Okay, but it's not that bad. What's the derivative of cosine? Negative sine, okay. Then you multiply, and then you plug this in, and then you multiply by the derivative of the inside function. The derivative of negative 1 pi over 2, that's just 0. What's the derivative of omega t with respect to t? Omega, right. That's it. This is going to be r times omega times the cosine of that. And over here, what's the derivative of this guy? Well, that's a 3. That's a constant. That's 0. And then you have just the derivative of r sine of this thing. Works pretty much the same way as that. And omega pops out, and sine becomes cosine. Okay? So, move out. I'm going to zoom out a little bit. Okay. So you get the r that comes out. I factor the r out of the whole thing, and then you get a factor of omega from the chain rule, and then cosine becomes negative sine, and sine becomes cosine. Okay. Everybody understand how that derivative came about? I'm seeing no questions, so I'm assuming everybody understands. Okay. Where do you go from here? Okay, so okay, so at 5 seconds and 10 seconds, what's the velocity? Piece of cake. Plug in 5 seconds into here, grind it out. Okay, so at 5 seconds, the r we know, the radius is 3 meters. Omega we already figured out is pi over 10. If I plug in 5 here, 5 times pi over 10 is what? 5 cancels, leaving a 2 in the denominator, so pi over 2, right? Pi over 2 minus pi over 2. That's the sine of 0. What's the sine of 0? Oh yeah, 0, right. Okay, same thing here, exact same thing. What's the cosine of 0? Oh yeah, 1. Piece of cake. So it's just 3 times that, 0 and 1. So the velocity is a vector that is 3 pi over 10 times j. Now, does that make sense? I'm going to go back. I'm going to put the drawing back up here. Where is this guy at 5 seconds again? Here's t equals 0, 20-second period. 5 seconds will be over here. Okay, where's the velocity vector pointing? It's got to be tangent to the circle, and if this guy's going counterclockwise, what direction is that velocity vector got to be pointing? Yeah, it's got to be perpendicular position, which is upwards, right? Okay, and if you remember from the other day when we went through this derivative, I said, okay, omega equals v over r. So v always equals r times omega. So the magnitude of the velocity is always equal to r times omega. So that's always going to be the magnitude, and you happen to know that it points in the vertical direction. That guy's got to be 0. So you could have just made that thing up. You really know your stuff, but you guys really don't know your stuff yet. So you got to go through the motions. This is important to learn this stuff. All right. Can you, with that in knowledge though, now that I told you that, what do you think V of 10 seconds is going to be? Here's where your knowledge of IJK notation and vectors and this business of R omega being the magnitude really comes into play. Anyone want to take a stab at that? Predict what R of V of 10 is going to be? Yeah, 3 pi over 10, negative 3 pi over 10 times I, exactly. Now, did everybody understand? What you can do is just, plug in 10, okay, 10 times omega is pi. Pi minus pi over 2 is pi over 2. Sine of pi over 2 is 1, and so that's negative 1. This term is negative 1. Cosine of pi over 2 is 0. This term is 0. So this term is going to be negative 1. So it's negative 1 times r omega, and then that's going to be 0. So you're only going to have the I term, which is going to be, but it's going to be negative, and the magnitude is going to be pi over, or r times omega. R times omega. 3 pi over 10. Hopefully that makes sense to everybody. This problem is good because it really teaches you a lot about IJK notation, what magnitudes mean of vectors. So it's a good thing to go through. Okay, so acceleration. How do we get the acceleration? Okay, there's the velocity. What do I do to get the acceleration? The derivative one more time, yes. So take the derivative one more time. And out pops another factor of omega. By the way, this is exactly the same stuff we were doing in the notes, right? And you've noticed that the V and the A have reverted exactly back to what they were before, right? The only thing changed by moving the coordinate system down is the position vector. The rate of change of things stays the same. I don't know if you noticed that, but this is exactly what we had before. If I take, well, almost the same thing. This A of t, remember A of t always has to point radially inwards. So that business of that 3 in this guy has got to go away, because then A would not point radially inwards. Okay. But anyway, works the same way. So there's A. The magnitude of A, right, is omega squared r. There's the omega squared r. So you could, again, fabricate these guys. Where's the rest of the stuff? Okay. You could go through and fabricate these guys if you wanted to. But if you just want to plug in the numbers, 10 seconds, right, at 5 seconds, right? Again, 5 seconds times pi over 10, that's pi over 2. Pi over 2 minus pi over 2 is 0. Cosine of 0 is 1. Okay? Sine of 0 is 0. So 1 and 0. And then this is the 3 times pi over 10 squared is the magnitude of A. And you notice that this thing tells us that it's going to be pointing in the negative x direction. So at 5, where's my drawing? Right? Hold on, let me put this back up here. So again, when this guy's over here at t equals 5 seconds, radially inwards we would be pointing in that direction towards the center of the circle. And that's exactly what is what gets tossed out of the equation when you put in the numbers. This is a quantity that points in the negative x direction, radially inwards. Okay. And then do 10 seconds. You could probably figure this one out. Which direction does this thing have to be pointing if you're up at the top of the circle? I left the vector hat off. Yeah, right. A as a to be drawn vector should be pointing downwards, right? Because that's radially inwards, up at the top. And you can see from the answer, negative something in the j direction, the y direction, no x component. So this is all consistent with what we learned before. Okay, that was a long problem. Lots of math, lots of vector math. Okay, so any questions about this? No? Nope, I'm scrolling down. Okay, somebody's typing something in. How did you take the derivative of v? Okay, so let's go back to v, right? V is r omega times the quantity, everything inside this parentheses, negative sign, this guy, I, plus cosine, this guy, j. Okay, so these are constants. R and omega are constants. They come outside the derivative when you're taking the derivative with respect to time. I didn't write this down. Yeah, I did. I should have written this down. I should have written down a of t, like I wrote down here. V of t is the time derivative of r, right? I should have written down a of t is equal to the time derivative of v. So maybe you want to, if you're taking notes on this, squeeze in equals dv dt with a vector hat for v. Okay, I kind of slipped up there and didn't make that quite complete. All right, so r and omega comes outside the integral. Sorry, not integral. Gosh, no, not integral. Please, not integral. Derivative. R and omega comes outside the derivative. For the first term, the negative sign comes outside, and we just have sine omega t minus pi over 2. So it's the derivative of the outside function. What's the derivative of sine? Cosine, okay? I pulled the negative sign out over here. That's where the negative sign went, okay? Which means I got to pull a negative sign out of this guy too, okay? So derivative of sine is cosine, right? But then we have to go back in here and use the chain rule and take the derivative of this inside function. The derivative of negative pi over 2 is 0. It's a constant. The derivative of omega t with respect to t is just omega, right? Use the power rule on t, which makes it go to 1. So there's an extra factor of omega that comes out. There's the extra factor of omega. It's no longer omega, it's omega squared now. All right, do the same thing on this guy. The derivative of cosine is negative sine, okay? So that means this guy should have a negative sign, but this guy had a negative sign, this guy had a negative sign, so I took the negative sign out here. That's where that negative sign came from. So now that's positive and that's positive, okay? So then you got to multiply by the derivative of the inside function. That's 0. That again, that's omega again. So you got another omega there. So this guy had an omega. This guy had an omega. I pulled the omegas out, and that's where the omegas ended up. Okay. So that's how that derivative works out. It's basic. It looks really messy because you got that ijk stuff in there, but it's basically just taking the derivative of sine and cosine along with the chain rule of the inside function, taking the derivative of the inside function from the chain rule. Yeah, I know. I kind of do that, and as we go forward in the course, I'm gonna be more guilty of that, especially when it comes to algebra. I'm just gonna say, okay, here's 4 equations. Put them all together in your head, and here's the answer. Because you practice this stuff enough, you really can get that good at algebra to do that kind of stuff in your head. You can actually get good enough at calculus to do integrals and derivatives in your head. You just got to practice. It's all about practice. Okay. All right. Well, that's as far as I wanted to go today. I think I did not mention this. I should have mentioned this. I put on a big set of projectile motion practice problems on the homepage. It's like 5 pretty long problems. And so take a look at those. They're just practice. They're not for a grade, but it's got the practice problems and all the worked out detailed solution. Okay. So try them on your own. I mean, remember, you got to practice this stuff, guys. So when I mean practice this stuff, I mean look at the problem without looking at the answer. Try and figure out the problem on your own without looking at the answer. And only if you get absolutely stuck to the point where you just can't figure out what to do, then kind of look at maybe the first few lines of the solution, see if it jogs your memory, and then try and complete it from there. Don't just go looking to the solution, because if I just tell you the solution, you really don't learn anything. It's practice that makes you good at this stuff. Okay? And that means doing the problems on your own without help. All right. All right, any other questions about stuff? We still got one more topic to go through before we end this unit. So I'll tell you what's going to happen after that. So just, what do we got outstanding? Just chapter 4 homework. It's the only thing that's outstanding right now. All right. So if there's nothing else that we need to do, any questions coming up? Other than that, that's it for today. We'll see you back here on Monday. Have a good weekend. Stay safe, guys.